All right, this is week 5, topic 1 for geology of the national parks. I'm going to start up with a little bit of recap. Last week we talked about weathering and erosion. Just as a reminder, weathering is the breakdown of rocks at the Earth's surface by the action of rainwater, extremes of temperature, and biological activity. It does not involve the removal of rock material from an outcrop. In that previous lecture we covered mechanical or physical weathering, which produces rock and mineral fragments that are identical but much smaller than an original rock outcrop. These types of sediments are called clastic or detrital sediments, and we classify those mainly by grain size. Sand, silt, gravel, those are all grain sizes for clastic sediments and sedimentary rocks. In this lecture, we're going to be talking about chemical weathering. So whereas physical weathering refers to the disintegration or disaggregation of rocks by physically breaking them apart, chemical weathering refers to the decomposition of those rocks and minerals as chemical reactions alter them into new substances. So we create chemical sediments by weathering, same way we create clastic sediments by weathering. So what type of weathering you get is going to be dependent on your annual temperature and your annual rainfall or general humidity. In a very hot and humid environment, you're going to have very strong chemical weathering and generally not so much physical weathering. In a very hot, very dry place, you have next to no weathering at all, apart from some physical weathering. And in a very cold, very rain, humid, heavy environment, you have very strong physical weathering, very strong erosion of your outcrops. There are 3 primary mechanisms for chemical weathering, all 3 of which include dissolution as part of the process. Dissolution is the dissolving of a substance into another substance, usually water. But we also have hydrolysis and oxidation as the other main components of chemical weathering. A chemical sediment is any atom or ion in solution, generally in water, and it is produced by all 3 of the chemical weathering processes, which again are dissolution, hydrolysis, and oxidation. We can see these different bottled waters in their quote-unquote nutrition facts have total dissolved minerals on the back of the water bottle. We can see this brand Arwa has a fair amount of calcium, magnesium, potassium, bicarbonate, can't read that one, nitrate, chloride, total dissolved solids. It's got a whole bunch of stuff in it in otherwise pure water. These dissolved minerals are naturally occurring and are inherent particularly in groundwater-derived water sources. Hydrolysis, in addition to producing chemical sediments, also produces solid grains, clay minerals. Hydrolysis is the process of water or carbon dioxide or acid breaking apart chemical bonds in minerals. So this physically breaks apart your mineral grains. As that occurs, you get dissolution, which is our new featured word for this lecture, and it is the process by which solids are dissolved and their components are dispersed in liquid. Clay minerals tend to be much smaller than the minerals they are replacing because of chemical weathering. You're taking a big solid mineral grain and breaking it apart into smaller mineral grains. In this microscope image on the lower right, we can see grains of potassium feldspar along the edges that have been altered into a clay mineral called kaolinite by chemical weathering. We can see how these kaolinite grains are much smaller than the rather large potassium feldspar pieces. Part of the reason this occurs is because rainwater in particular is slightly acidic. Carbon dioxide gas, which is naturally present in our atmosphere, will dissolve within that rainwater and chemically react with the water to create carbonic acid. So in a drop of rainwater, you have mostly regular water, but you also have carbonic acid and free hydrogen ions. These free hydrogen ions and carbonic acid will react with your feldspar, which is potassium aluminum silicate, and that will create a clay mineral, aluminum silicon oxygen with a small hydroxide group. Notice that the potassium is dissolved away. It becomes dissolved in the rainwater after passing through the mineral grain. And so does some silica. Silica and potassium dissolve fairly readily into water. Our third process, oxidation, also produces solid grains, iron oxides. For example, if you take a lump of the mineral pyroxene, which is iron silicate, and you add water, you end up with a silica, because that dissolves in water, and you end up with an iron ion. That iron ion will react with oxygen, which is present both in the air and in the soil, and that will react with naturally occurring water, both as water vapor and as water liquid, and that will create iron oxide, hematite. So your oxidation breaks apart your pyroxene into a silica and an iron oxide. This very process is part of the reason we know that there was liquid water on Mars. From this very up-close photograph, this scale bar at the lower left is 1 centimeter, so it's very small. We see an outcrop on Mars. And we can see from this outcrop that there are all of these little slots that are circled in orange, and these are the places where former mineral crystals used to be. They were dissolved away by water on this outcrop. We also see these round concretions, they're called which are colloquially called blueberries. These are little spheres of iron oxides that precipitated directly out of water while this outcrop was underwater. And that's one of the proofs of liquid water having existed on Mars. So to recap, our products of chemical weathering are chemical sediments, which are atoms or ions dissolved into solution in water. We have oxide minerals, such as iron oxide, and we have clay minerals. Now, a clay mineral is a bit of a colloquialism. Clay is a size of grain, but it's also a style of mineral. And so those are our 3 products of chemical weathering. You can see on this top image clay-rich weathering rinds containing some iron oxide minerals and some clay minerals on these rounded basaltic cobbles in the Columbia Gorge. The Columbia Gorge is cold and wet, so we end up with very high physical weathering and some chemical weathering. And so we have these cobbles which have been removed from their outcrop, and rainwater has seeped into the outsides of these cobbles, chemically altered them, and produced this weathering rind. This lower picture shows the propagation of a weathering rind in a sandstone from eastern Oregon. And we can see that it forms this oxide-rich orange band around the otherwise gray piece of sandstone. Chemical weathering only works on surfaces. So if I go back to this one, our weathering started at the surface and is seeping down into the rock because the chemical weathering produces new surfaces, very small ones that just allow a small amount of water to enter into your pore spaces in your rock. But mechanical weathering breaks rocks into smaller pieces, which exposes more surface area to chemical weathering. As your rock pieces get smaller, their relative surface area increases dramatically. And this allows for more space for chemical weathering to occur. But these processes don't work in isolation. Stress, tectonic stress, will fracture your rocks and create cracks. That's a part of physical weathering. And mechanical weathering gets concentrated on those fractures, cracks, or joints. And this creates new surfaces for chemical weathering to occur. We can see in these 2 diagrams that weathering is very strong along those fractures, and those fractures are allowing water and air into the subsurface, into the unweathered rock, and allows weathering to occur along those surfaces. Part of this is a process called spheroidal weathering. Chemical weathering attacks the faces and sharp corners on the sides of pieces of rock. It attacks the face on one side, the edges on 2 sides, and corners on 3 sides. So these sharp edges, and particularly corners, gradually round out over time as those sharp edges weather down chemically and mechanically into these spheroidal shapes. We can see these 2 outcrops down below. On the left is Joshua Tree National Park, where fractured granite rock has allowed chemical weathering to round the large blocks, which were separated by joints in the granite, into these rounded boulders. We can see this in action on an outcrop of what looks like basalt here on the lower right, where we have some more angular blocks still in the hillside, and some of these more rounded, spheroidally weathered boulders still in the outcrop. Chemical sediments ultimately form rocks by precipitating out of solution. Here we can see calcite, a mineral, precipitating directly out of this water droplet to form something called a soda straw, which is a type of cave formation that I'll talk about in more detail shortly. But we can see these sharp angular edges of this crystal, which is growing into this water droplet. We can even see small pieces of calcite suspended in this water droplet a little bit further below. Chemical sedimentary rocks are classified by their chemistry as well as by the process that makes them. There are three main kinds. There are chemical, biochemical, and organic sedimentary rocks. So we already talked about sedimentary rocks made of clasts. That's going to be your sandstone, your conglomerate. Now we're talking about sedimentary rocks made of other stuff. Chemical and biochemical rocks form when ions or atoms are precipitated directly from solution. So they're taken from being dissolved in water and they are deposited as a solid. The difference between the two is that biochemical rocks need an organism to do the precipitating. Think of shell growth. A snail is taking calcite ions directly from your seawater and using it to build its shell. And that is biochemical precipitation. An organic sedimentary rock is kind of an oddball in the world of sedimentary rocks. They aren't produced from sediments derived by weathering, but instead from organic material that has undergone the same sort of burial, compaction, and changes in temperature and pressure that lithify sediments. So if you take a swamp or a big pile of leaves, you add some heat and pressure, you add some time, you compact it, you will eventually get an organic sedimentary rock. This happens a lot in marshes, like a peat bog. Peat becomes lignite, which becomes coal, which we see up here in the middle, that flammable rock. Three types of sedimentary rocks are fossiliferous limestone, which is a biochemical rock. Coal, which as I said is an organic sedimentary rock. Not a mineral, it's a rock. And then rock salt is an example of a chemical sedimentary rock. Salt ions are deposited on the ground or as a rock as water evaporates over time. And that deposits the salt as a layer on the bottom of a dry lake bed, for example. So let's talk about calcite a little bit, that mineral I've mentioned a few times. It is the primary component of a rock called limestone, which can be chemical or biochemical. Here we see three flavors of limestone, one that is fossiliferous on the left, one that is fairly plain, so that one's going to be more chemical limestone. And then above that, we have one that looks like it's made of a whole bunch of tiny nodules. That is called an oolitic limestone, and I'll talk about that in a second. A biochemical version of limestone would be like dead plankton accumulating on an ocean floor, or a coral reef, or deposits of marine shells. A chemical version of limestone would be precipitated out of mineral-rich groundwater, which we call travertine. Small nodules precipitated out of warm seawater, which we call oolitic limestone. And we also see it sometimes in drying up lakes or ponds. As the water dries up, the calcite gets precipitated around the edges and bottom of your water body. Now let's talk about quartz or silica. While quartz is a primary component of igneous rocks, we also see it in sedimentary contexts. It makes a sedimentary rock called chert, which can, again, be chemical or biochemical. In this image, we see a biochemical chert, which is deposited by something called a radiolarian plankton, which is a type of plankton that has a shell made of silica. It actually has a very small microscopic glass shell. When you get a big deposit of a radiolarian plankton, you get a layer of chert forming on the sea floor. A chemically deposited quartz would be something like the inside of a geode or an agate or a thunder egg. In that case, it is deposited as a layer inside of a void that is saturated by groundwater. It can also replace minerals that are more soluble. In some types of geodes, soluble minerals like oxides will be completely removed by chemical weathering, and then quartz will be deposited on the inside of that nodule where those oxide minerals used to be, filling in the space and creating bands of layered or crystallized quartz. And that's how geodes form. So let's look at this limestone outcrop here from Death Valley. We can see this gray rock with those fine layers called laminations in it. That's a limestone made up mostly of dead plankton. It also has these dark brown or black layers of chert in it. And these are our layers of biochemical chert, biochemical quartz, that is deposited in layers in this limestone. The different layers in this limestone merely reflect different changing conditions in the ancient ocean this rock was deposited in. And that can be temperature, it can be climate, it can be changes in ocean currents. Those changes in the environment are always reflected in the rock in some way or another, whether or not it's visible. Here the changes are visible as changes from limestone to chert and back to limestone. Now let's talk about some of my favorite types of chemical sedimentary rocks, evaporites. These are rocks that form when evaporation concentrates chemical sediments, causing them to precipitate. The classic example of an evaporite environment is going to be one where a lake is drying up. Let's talk about something like up above here. We have the Great Salt Lake in Utah, where we can see salt being deposited on the bottom of this salty lake. The Great Salt Lake has no outlet, so all of the water that falls as rain in its drainage basin ends up in the Great Salt Lake, and so do all of the chemical sediments dissolved in that water. As your rain causes chemical weathering in the surrounding mountains, it then transports your dissolved atoms into the Great Salt Lake, where they remain. As the water evaporates over time, those salts are concentrated and deposited as layers on the bottom of the Great Salt Lake. We see evaporites forming most often in dry or hot desert environments. But you also find them in areas where basins are sometimes filled up by the ocean and sometimes not filled up by the ocean. Down below we see there's this smaller basin separated from the main open ocean by this small ridge. And as ocean levels rise and fall over geologic time, that basin will sometimes be connected to the ocean, which allows new water to come in, and sometimes it will be disconnected from the ocean. And during that time, the water will dry up and leave behind salts or evaporite minerals on the bottom of the basin. Then the ocean will rise again and flood that basin, and it will deposit more mud and add new minerals that will then be deposited again as the sea falls and it dries up again, and you can picture that cycle repeating over and over again to create deposits of evaporites. One of the most important evaporites is rock salt, which is also called halite, and it is salt, the same kind of salt you get on your table, and it is precipitated from solution as water dries out. In the U.S. national parks, the best place to find rock salt is in Death Valley, at the Badwater Basin, the lowest point of Death Valley, 282 feet below sea level, where all of the water that falls as rain in the surroundings ends up here in the bottom of Death Valley. And because that's a very hot, very dry place, that water will very quickly evaporate and leave behind layers of rock salt on the valley floor. Another important evaporite is gypsum. This is a calcium sulfate mineral, and it is a rock that is also precipitated out of solution. It's another evaporite. In the national parks, this is most often found at White Sands National Park, where the sand dunes are actually composed of gypsum sand, because the surrounding mountains contain large amounts of evaporite rocks from an ancient sea that dried up. As that ancient sea dried up, those evaporites became solid rock, mostly gypsum. They were then uplifted, and those gypsum sediments are now deposited in another closed basin, much like Death Valley, with no outlet, and that gypsum is precipitated on the valley floor, and you get both crystals of gypsum and sand of gypsum, which blows around and makes the world's largest field of gypsum sand dunes. These are some organic sedimentary rocks. This is a layer of coal in outcrop, that black layer, underneath layers of sandstone and shale. This is that process I talked about earlier, where you have peat, which is compressed moss, essentially, gets buried and compacted into a thing called lignite, which is soft brown coal, moderately energy dense. When you compact that more, you get a very dense rock called bituminous coal. That's the kind of coal you most often see used in power plants. When you compress it even more into a metamorphic rock, your bituminous coal becomes a thing called anthracite. This is the very high quality coal. This is the kind you want to use in electricity. This is the kind that gets used in steel production and other industrial processes. However, it is entirely derived from compacted peat moss and other swampy deposits of organic matter. So at this point, we've learned that calcite and limestone form from minerals coming out of solution of water. Now, what happens when you re-immerse those same chemical rocks in water? You may recall that rainwater contains carbonic acid, so what happens when you combine carbonic acid in rainwater with the calcite present in limestone or dolomite or other chemical sedimentary rocks? You get the dissolution of that rock. That rock will dissolve back into the water. Now, limestone is probably the most important chemical sedimentary rock that is subject to dissolution. Limestone rocks will form landscapes called karst. A karst is a topography formed from the dissolution of soluble rocks, such as limestone, dolomite, or gypsum. It is characterized by underground drainage systems with sinkholes and caves. That's a nice, succinct definition of karst for Wikipedia. And we can see a cross-section here of a karstic landscape where the limestone bedrock is riddled with caves, the surface is pocked with sinkholes. You have areas where you have caves forming and then collapsing, causing sinkholes. Streams will appear and disappear from holes in the ground, and caves are definitely present and part of the regional aquifer, which dissolves the limestone as that meteoric water from rainwater slowly dissolves it away over time. The USA has a lot of karstic topography in it. These are places where we have carbonate rocks, such as limestone or dolomite, at the surface. And where you have carbonate rocks at the surface combined with ample rainwater, you get karst. This is a map of the karst in the US. All of the green rocks are considered karstic. And these are places where caves are very abundant. We can see a lot of it in Texas, New Mexico, Missouri, Kentucky, Tennessee, all throughout the Appalachians, throughout areas of the Rocky Mountains. These are all places where caves are present. Underground, we have a thing called the water table, and this is the underground zone where water saturates everything, and there is no air present at all in the subsurface. This saturated zone, also called the water table, is where caves are forming, because your fractured limestone is completely covered in water that is actively dissolving it. So cave formation happens in the saturated zone, in between your porous rock, which is not saturated with groundwater, and your impermeable rock below it, in which there is no water because it's impermeable. Some features of karstic environments, as I already mentioned, are sinkholes, springs, and disappearing streams, things called solution valleys, which happen when a whole bunch of sinkholes line up together, and you get caves with cave formations called speleothems. These are stalactites and stalagmites, which we'll talk about in more detail shortly. We can see in these four images the evolution of a karstic landscape. Up above, we have a young karst landscape where we have a disappearing stream, where a stream will just disappear into the hole in the ground. We have lots of sinkholes, but as that, we have lots of caves underneath it, but as that landscape evolves over time, then we have caves forming solution valleys where a cave might just collapse and create a long valley. We have these sinkholes merging and forming larger valleys that are caused by the dissolution of that limestone. All of that rock dissolved away and was later transported away by water in these drainages. Over further time, you end up with something called tower karst, where you have even more dissolution of rock, and those former sort of mesas or areas between your sinkholes are left behind as tall promontories. We don't have very much of this in the US, but it is common in places like China. Let's talk about how sinkholes form. Now. Water will percolate down into your bedrock and form voids. Form voids as your limestone slowly dissolves. Over time, the pathways that water is traveling through will open up and start bringing dirt into those voids. Eventually, those voids will become bigger and coalesce and form a large cave underground, while the ceiling slowly collapses above it and migrates toward the surface. Ultimately, the ceiling becomes too thin to support itself and it collapses, forming a sinkhole. Now we're going to talk about the most important cave anywhere in the world, possibly, Mammoth Cave National Park in Kentucky. Mammoth Cave is the world's longest cave. Before I tell you how long it is, take a second to think about how long you think it is. These pictures show you what Mammoth Cave looks like. It's mostly bare, unadorned rock, but it does have some areas of nice cave formations, such as this flowstone area. Mammoth Cave is allowed to become so big and long because it is protected by a cap rock of sandstone and shale. Underneath the sandstone and shale is a thick stack of limestone, and these are where the cave passages form. The sandstone and shale does not dissolve, so it forms a nice, hard, resistant rock that protects these caves from collapsing, and protects a large area of large caves. Mammoth Cave is over 426 miles long. That's a very long cave. That's a lot of void space underneath this plateau. Now there are two cross sections here. The gray rock at the top of this cross section is that sandstone and shale, which is insoluble and slightly permeable, which allows the rainwater to enter the limestone and dissolve it. The plateau Mammoth Cave is located underneath is created by that sandstone. However, that sandstone is not present on the nearby Pennyroyal Plateau. It's separated by a series of cliffs called the Chester Escarpment. So you have the Mammoth Cave Plateau, where you have the cave area protected by the sandstone and shale, but where that sandstone and shale is not present, we have a karst landscape with limestone at the surface. And by looking at that Pennyroyal Plateau, we can see all of the sinkholes and solution valleys that are present in that very rough, undulating surface. These occasional ponds that are present shows you the surface of the water table on that plateau, so it's very shallow. This is an example of a disappearing stream, two examples of disappearing streams actually, where a stream just disappears into a hole and vanishes underground. Again, very common in karst landscapes, particularly in central Kentucky. This is the outlet of a river called the River Styx, which flows through some of the lowest levels of Mammoth Cave. This river drains large areas of Mammoth Cave and re-enters the Green River. So areas that are being drained by the River Styx are actually no longer forming as caves because they are full of air instead of water, so no limestone is being dissolved. The areas that are still underwater, underneath the River Styx, underneath the regional water table, are places where caves are probably still forming underground. So now we're going to talk about cave formations called speleothems. These are deposits precipitated from groundwater. Most of them are made of a thing called travertine, which is a type of chemical limestone. It's deposited by calcite precipitating directly out of groundwater. Some examples of speleothems are stalactites, stalagmites, soda straws, columns, draperies, helictites, rimstone, flowstone, and many other highly specific formations that we find in caves, formed by dripping or slowly flowing groundwater. A lot of things start out just like this, as tiny mineral grains of calcite precipitating out of small droplets of groundwater that have percolated through the limestone and reached the roof of the cave. Remember, CO2 from the atmosphere and from decaying plant matter gets dissolved in percolating groundwater, and that causes the limestone to dissolve. That dissolves calcite directly into the groundwater that is then dripping from your cave ceiling. As that water drips down from the cave ceiling, it leaves behind a thin layer of calcite, and it also deposits calcite on the floor of the cave, or a stalagmite, creating a small pile of calcite that will grow upwards over time, and that's called a stalagmite. Stalactites, the ones that hang down from the ceiling, C in stalactite for ceiling is how you remember that. Most of them start out as things called soda straws, which are basically miniature versions. We can see these soda straws, which are hollow tubes of calcite delivering droplets of water to their bottom. We can see a whole forest of these soda straws in Carlsbad Caverns on the lower right here. So stalagmites and stalactites are the most famous cave formations. Stalactites hang from roofs, commonly made of calcite or aragonite, usually pointed. Stalagmites tend to be rounded and grow up from the ground. The word stalagmite contains a G for ground, so that's an easy way to remember it. In these two diagrams, we can see the formation of stalagmites and stalactites. They create a distinctive layered limestone that we call travertine. These are located in Carlsbad Caverns, which is a national park I'll talk about in just a couple of minutes. And here's a stalactite that has been cut in half, showing those concentric layers of these features growing over time as thin layers of water deposit thin layers of calcite. So now here's Carlsbad Caverns National Park in southeast New Mexico. It's a fairly large cave, and it houses a very famous bat population, seen here in the top right, that enters and exits the cave en masse every night, and then it re-enters the cave every morning. So that's a very popular activity at Carlsbad Caverns, is watching the bats leave and escape out of the large, really huge natural opening to the cave. Carlsbad Caverns is particularly notable for having the largest cave chamber anywhere in the USA. It's 4,000 feet long, 600 feet wide, and 250 feet high. You can fit a sizable portion of downtown Portland inside the big room. The big room is richly decorated with stalagmites, stalactites, and columns, which are what happens when a stalactite and a stalagmite meet and form a continuous pillar. Now, notice that Carlsbad Caverns is located in New Mexico, in the middle of the desert. How does such a large cave form in a dry environment? Well, it formed over about 4 to 6 million years, which is pretty quick for cave formation. But the main cave formation has been via dissolution of limestone, as is expected, by sulfuric acid dissolved in groundwater, rather than carbonic acid dissolved in groundwater. So why is there sulfuric acid in the groundwater at Carlsbad Caverns? Well, it sits above petroleum reserves. And petroleum reserves, that is oil and gas, contain appreciable amounts of hydrogen sulfide. This slowly migrates upward from those underlying petroleum deposits and combines with oxygen in groundwater to form a weak sulfuric acid. Sulfuric acid is a much stronger acid than carbonic acid, so it dissolved these caves much faster than you would normally find in somewhere like Mammoth Cave. These are some particularly large stalagmites we can find in Carlsbad Caverns called the Hall of Giants in the big room. And here on the right, you can see layers of travertine in a stalagmite that has been taken from a microscope. Here are some columns which again form when a stalactite and stalagmite meet. Some very tall ones in the big room, some of which are 200 feet high. On the above left, this is called the totem pole. Above right, this is called the wizard's staff, and it's weird because it's made of gypsum. Because of the dry climate at Carlsbad Caverns, it contains a lot of formations made out of gypsum rather than from travertine, calcite. And that's mostly because of the sulfur present in the sulfuric acid, as well as the dry environment allows those to form. This is in a different cave called Lechuguilla Cave, which is also in Carlsbad Caverns National Park. And on the lower right, we have the Temple of the Sun, a large, broad stalagmite that reaches up to the surface. Some of the other famous formations are called draperies, which are basically slanted stalactites. When you look up at them from below, you can see they tend to be kind of squiggly, but you can also shine light through them because calcite is not an opaque mineral. It allows light to pass through, and you get these beautiful draperies formed in some areas of caves. A particularly weird one is called a helictite, which extends out of the base of a soda straw. So you've got your thin tube extending down from the ceiling. Now what happens if you get a perforation in that tube? Well, if you get a small enough hole in your soda straw, the water is drawn up through it through something called capillary action. In a narrow enough tube, water will move vertically through that small hole, and that's called capillary action. So capillary action will allow smaller tubes to come off of your main soda straw and form these weird squiggly upward shapes rather than just dripping straight down. So these are formed very, very slowly and are extremely delicate. And that's all for caves and karst. And that's all for topic 1 of week 5. Stay tuned for topic 2.